And we're going to talk a little bit more higher level of the stack. A lot of stress and tutorials lower the stack. So this is more about how bringing the lower the stack algorithm, foundation models, whatnot, up and out the massive more from the insight reporting standpoint. So we will cover some of the interfaces below as well. It's a little bit about me. I've 4 software ventures, mostly enterprise space, 3 software reporting oriented, 1 security, led various teams internationally and locally. My claim to fame is I can sleep on the airplane, very nice superpower, and I've interfaced to 50 different databases, lots of different GenAI services. We'll see that now as we go through this. I also enjoy mentoring universities, whatnot, to share my knowledge and actually learn what's new on the horizon. So why Milvus as a database? For us, our main concern is bringing the value of the stack now. Milvus is a very scalable database. It's really flexible in how you configure it, how you deploy it. In our world, we use the Milvus Cloud as an option and not the open source locally available version. We also like the multimodal support and sort of the capabilities of lovely cats and whatnot that we see in the future examples. So it's more than just text, also image. Also, the ability to store JSON, arbitrary JSON is really important. So it's nice to be able to just store stuff and not worry about changing tables, columns, and whatnot in the relational world. So just store is a wonderful thing. Okay. So what I've seen in the past, most of my software ventures, and a lot of the tools today, modern databases, are really, really efficient for developers to get stuff working very quickly. Great, and display stuff. And users like it, they like functionality, and within 2 weeks they're busy saying that's great. I really want to go report on this stuff, get the data. I want to do this report, I want this format. The analysts, the end users, whatever, they all love the app. Then they start clamoring for the data. Big record scratch moment because they don't know how to interface with Milvus. It's not your language speaking. So it's really painful. And what we've done in the Qarbine world is sort of try to balance those 2 sets of stakeholders between those who know how to query and those who know the business, and let them each do what they're really good at. Yeah. So we're able to be embedded as well, not just from a tooling standpoint. So where we fit in the whole enterprise stack, there's a lot of BI tools out there. There's a lot of good summary visualization tools that are very people-centric, great to the relational database. But if you have Milvus or other modern databases, they simply don't work. Language querying is usually not SQL. Trying to use SQL on some of the gateway, it's really painful as you use JSON a lot. Close the answer set in a ridiculous manner. So we're not just about summary visualization, but we really excel more than detailed analytic reports. So totals, subtotals, interactivity, percentage totals, the whole 9 yards. The reason a lot of this feature is here is that most people on Wall Street use reporting using number 4 to do their work. And that sort of addressed the impedance mismatch of an object-oriented language and relational databases. Now we have modern databases and to use lengthy SQL tools and doesn't fit, whereas we're purposely built to handle these situations. And we can be deployed either in an embeddable fashion or, again, the whole desktop tool suite has that individual. Okay. So architectural-wise, we have our tool suite there. Our backend is Node.js and Express. With a set of modular services. AI being one of them, is a whole bunch of 100 different APIs, and various modular database drivers. In this case, we're talking about Milvus. So all that sits either AWS or Azure. We are deployed as an AMI in your VPC. We are not a SaaS provider. This Goldman Sachs is never going to throw their data to us. Okay. So the tool set, we have querying tools, we have analysis and reporting types of activities for formatting, data, return, style sets. It's a whole suite that looks like a Microsoft Office but built for modern data querying and presentation. Okay. The other thing to note is that we separate out querying from the analysis. What that does is let the people who know how to query a modern database, with syntax, whatever it is, write the queries, store them in our catalog, and then the analysts and others can come along and cherry pick. Yeah, that's the type of data that I want. They don't need to know the syntax. They can move along with the data at hand. And then the developers aren't in the report writing business. The analysts are in the business of doing their work, and no one needs to go and learn a new SQL language. And then the system administration, that's where we configure to build this and then AI service. So who's using Milvus right now out here? Anyone? Okay. How about Node or JavaScript? Okay, we have one. Okay, not JavaScript and Python probably. Fair enough. So we are again Node.js based. So in that environment, this is how you generally set up a client and query. There's lots of different options. Obviously, this is not at all like your traditional query language, or like the base Unstructured, if you will. So it's pretty raw. Okay, for most candidates, they're not really interested in this. When you add some of the other parameters with the GenAI world, it gets even more complex. Not really approachable for the non-geek in us. So a very simple version would be querying some collection name similar to a table name. So very simple filter, and then you indicate what your output fields are, like your select flows. Okay. I'll share these. So there's some links there for the different SDKs. Again, we use the Node world. So on the vector side, this is the API to use vectors. Everyone's familiar with vectors? You might expect that. So this is the call to do a search with vectors. So in general, you have a magical vector number. We go to Milvus, it does the thing, and the outcome answers that some sort of JSON and everything. We're perfectly fine with whatever the shape is. A very simple search API would be searching, again, the collection name, what output fields, give me all of them. If you do that, you'll also get the Milvus score of distance as part of the answer set. And then they are a rudimentary type of expression which sort of maps that to a where clause, or kind of, for the most part, and a limit as well. Again, that's sort of like a SQL limit concept. Okay. So things to keep in mind, vectors are usually not needed as part of the answer set. So the default Milvus answer set includes all the vectors. And usually you don't need 1,024 numbers part of your JSON answer set to do whatever your business application is. We, by default, toss them just to save you on the bandwidth. We use API version 1, the version 2 gets out, found a bit of inconsistency, so we're still in version 1. This is the general flow. So if you were to have, in this case, we have a Qarbine no-code dialog, if you will. It actually supports lists, granular buttons, checkboxes, the whole 9 yards. But for this example, we're just entering a random phrase, right? So the user enters Python, it goes into our back end. The query on our side just literally has near text, and that sign references a variable. In this case, the user prompt here is Python. We're going to then hit OpenAI, hit the vector, back into our world, formulate the final query, hit Milvus comes back with the answer set, goes into our central processor, which defines how to iterate through the answer set, format things, and voila, we have a result, analysis result. And this result, you can go and copy things, click things. It's a very interactive reporting environment. It's almost like we can build the web page for you in one case. You don't have to hand code it. Okay. So the benefits here, so Milvus is very powerful as a database. OpenAI is very powerful to provide embeddings. So we sort of marry those two and bring it up so that you can go and embed this minus that if you want into your own application. You're not going to be in the report writing business. You can go and focus on innovation that your customers and users really want. The nested JSON is perfectly fine with us. A lot of the tools out there will just follow their base more complex it gets. And then it's basically up to the developer to basically unpackage and repackage things along the way. So it gets really painful. So it really helps everyone, the analyst and the developer, really deploy types of applications are very informative. So one thing we did early on, you saw that the syntax for querying this. Well, that's not really approachable for most people, and me too. I'm like to be lazy, trying to SQL on many different languages. So we ended up creating a SQL-oriented like syntax for Milvus that ends up translating this into that. So we're always native down low. You can always go down low to get to whatever Milvus provides, but up high, you can write it a little more approachable. You're not busy squinting and trying to match up double quotes and single quotes and all that lovely fun. So it gets very easy. So some of the nuances that we found with Milvus is that in this world, if your filter had an and, it's case sensitive. Go figure. Same thing with knots and word as well. Whereas in our world, we sort of like you can word here and you want, in which case it will yield it properly. So there's some slight nuances in the API that we found as well. The other thing we can do is dynamic query vector. So given this, we get an alternative is to say near text. So it's like the Python example first case. We will behind the scenes go and hit OpenAI for you, get the vectors for the Python in this case, and then shove it back in to the actual query right there, and then run it for you. So again, you don't have to do a whole lot of heavy lifting just to do things that really should be. The other thing we've done is what we call dynamic RAG analysis. And in this case, we have queried Milvus, getting the answer set back, and we're starting to format the result. Okay? So we start formatting the header, so it's not this direct to eventually state. We format that much. Then we start formatting the group, in this case, the stock group, a lot of stock portfolio examples. What we can do here is take that text and use it as part of a prompt, right, as we're formatting. So we can call this macro function that looks like so. So comment on the stock diversity of this portfolio, yada, yada, yada. Take that text, append it, give it to OpenAI. Okay, it does its thing, comes back with some commentary, and just include that right in the result. But this is like so simple, you can do RAG, like a one-liner macro, literally. And you can include that. The backend can be public LLM, private, doesn't matter, it's just the way. Most of the APIs are fairly standardized when you're at OpenAI in flavor. There's really only two, either completion or embedding. The other thing we did was provide interactive RAG. So just ask AI. So that will, like on there, we could be looking at a result and put there, and we can just simply say summarize this, and we say, well, how about all the pages summarize, right? Voila, we hit OpenAI in this case, and the data includes information on 3 articles, et cetera, et cetera. So be able to use RAG on the fly at the end gives you a whole lot of flexibility to do AI stuff. So one of the side benefits we got through developing a SQL interface in our world is that some of our tools, of the like 10 different tools, some of them can automatically generate the query for you. So we hook things up so that this is query by example, where you literally like type in stuff and it'll formulate the query for you based on whatever the data is. In this case, we chose Milvus as the backend, but we're generating the SQL, and then again, we'll do the covers, convert that to the raw JSON thing. So type that in, you nicely get good, hit the go button, and voila, there's our answer. But you're not going to know a query on summary step. We'll do it for you. The other thing, this is pretty common now for pilots for most of the databases out there. There are a dime a dozen. So we've done it also with the Milvus world. And again, so in this case, we have quick setup with one standard Milvus databases out there. There's also medium articles we saw output from before. And we typed in, find all the items with the color starting with red. using SQL syntax, use the table name of quote, quick setup in the SQL. We hit OpenAI, we send the prompt over, and voila, it says select star from quick setup or color like whatever. Now, our experience with a lot of the LLMs, you need to sometimes handhold them, and then they just go down in some bizarre direction. But they get you sometimes in the right area, and then you edit it and fix it. So trying to get like the near text that I have an example of, it took a long time, and then eventually just gave up. We hit Anthropic, we hit OpenAI, we hit the Azure, hit Bedrock, and none of them, even though we saying in my head, like, use this near text function, it still didn't quite get the right thing. So your mileage may vary with the types of prompts you enter, and also with the depending on what LLM you use. So this is where we're at. If you want information on us, we're here. Milvus does have several types of offerings. The Tree Cloud is very nice. There's sample data that's really, really nice to use to figure setup, and also the Medium articles. There's an online console. There's a lot of tutorials as well. Just take advantage of them. Some of them are new, some of them are Python. Pick your language of choice. We found it really quick and convenient to go and really get the value of Milvus up and out, and then be able to embed whole GenAI and vector databases within the application. How are we doing on time, Tim?
Oh, you got a couple minutes.
Okay, so I'll just, I haven't live, we can do that offline in the interest of the time. Are there any questions on anything that is very quickly covered? Okay. So we're very horizontal, so we don't really know what we're doing, but healthcare is using a lot for the multiple search. A lot of people are doing multimedia entertainment in the world. It really runs the gamut. We're specifically not doing a chatbot. That's lazy, right? That's doing patch, but we sell that. But for you and whoever's out, just experiment with fun stuff. Get motivated and see what's out there. Because they're really easy. There's tons of different services that are effectively great. So like my OpenAI account, I don't even know if I spent a penny on it. Rounding up. I don't know. Zillow is free. Lots of other database videos have free options. Most of them have some GenAI capability. Find something fun and have at it. Learn. Best way to do it. And also, a lot of them have Discord or equivalent. So just ask the community. They're really good about answering. Go from there. Okay. Anything else? Anybody else? Yes.
Curious, do you have any competitors?
Oh no, zero. So our typical competitors would be the legacy SQL tool, which are basically clueless about vectors, let alone the query engines. The developers themselves are competitors. We're trying to help them. Like, do you really want to write a reporting? The answer is no, unless you're insane. Do you really want to write a database? No, unless you're insane. So there are some SQL gateway like things that I don't know who actually wants to build this correctly. But like certain other databases across town, University, they have a SQL connector, the I connector. And with that, you can get to your data, but the more you use JSON with embedded documents and embedded arrays, most everyone wants to just flatten the answer set because it's SQL. It has to be flat, it has to be completely. So what happens here is it just explodes. You embed a document, it explodes. Embed an array, it explodes, it goes on. So you start with what should be, like in our world, we get a document, pull thing back, and it's embedded JSON. This is perfectly fine. Whereas everyone else is going to take that perfectly one good row, actually the answer set, and explore that into God knows how many rows. Because it has to satisfy the homogeneous type of ordination. Then you get it back and say, that's great, but now you could rebuild what was perfectly good to begin with, the database. That just seems crazy. So that's I think the state of the art. But again, I've done 6 of these, 5, 6. So that's my view. Anybody else? We move on to the next one.
So what is it for? Because you have to report. So when you in finance, they ask for very accurate number. So when you use the AI, they actually use analysis.
Well, yeah, your mileage may vary, and there's a big disclaimer, right? Those things you have to know. And
so you probably come out of currency accurate. Oh, they keep about the same they actually use for it.
okay, so there are some services now that are being offered that are the guardrail services that will try to handicap the output of one LLM. And sometimes they'll go and take that out from one LLM and put it into another one, and if the other one's opinion to then render a verdict on whether that first LLM's output is reasonable.
You probably use the currency. So I use them, they do the currency. When they do potential, they have to
Ideally, yeah.
they do that. Do this especially because they are the model they are after when you use the promote is actually when you change the model, the promote is actually so how do you actually use how do you actually
So we don't. It's up to the client's burden to bear, right? We're just interfacing with the LLM. And a good example of what you described is the LLM learns stuff and it's a legal element, right? In January 1, there's a change in the law. If unlearned, all these things will allow prior to January 1 is suddenly not allowed, or vice versa. And there's out there approaching small language models and large language models that are addressing the how to keep it up to date and keep it factual without hallucinating. Anybody else before we move on? Very cool. Thank you all.
Okay, next up, we have a very interesting talk from GenAI. So this is the next lecture. Which we stop. Do you have you got Zoom up? Yeah.
I have it running through the browser. Is that okay?
Yeah, however you want to do it.
Is it good the way it is, or
Let me just join the audio. Share your screen. Get permission here.
Oh, oops.
The audio, maybe we could get the audio from mine.
Fine.
Because you change your permission.
Until it is quit.
Yeah, just.
I guess I need to go back into it.
Yeah, that's how.
That's okay. It's not a big deal. I have the On that, yeah, let me pass. Share the screen. And you do the thing that you do.
And this should work.
That should work. Let's see. Oh,
All right, awesome. Hey everybody, my name is Nolet. I'm here from just outside of Annapolis, Maryland. Coming here to talk to you guys today about our work accelerating Milvus on the GPU. A little bit about myself. I am a principal engineer at NVIDIA. I've been there for about 6 years. Vector search has been my life pretty much the entire time being there. I started out writing a library called cuML, which it turns out relied very heavily on vector search. And then LLMs came along, and OpenAI came along, and everything kind of exploded for vector search. And now I'm spending a lot of my time leading teams and leading the infrastructure for vector search at NVIDIA. I'm going to go through 3 main topics today. I figure I should probably introduce the library that we've created specifically for vector search at NVIDIA, and then I will dive into our Milvus integration with our library. But first, I'm going to give a brief overview of kind of the GPU and what's vector search and all that. I can skip parts of this if everybody's already familiar with this. So who here is not familiar with the concept of vector search or knows why we would do vector search? Anybody? This is nothing new to everybody here, right? You want to search for a bunch of vectors in a big pile of vectors. You want to find the closest neighbors. It's a lot different problem than a typical database search when you create an index in a regular database, like a relational database. Generally, it is what's called runtime, right? You have a specific insertion point where you can start seeking to and search, and then you have usually a well-defined endpoint. Unfortunately, you can't just sort the vectors and start at a specific place in the database. You need to compute distances between vectors, and we have optimized ways to do that. So maybe a little bit more formal definition of vector search to kind of scope it a little bit about what vector search is and what a vector database is and how the two differ. Because a lot of people hear vector search today, they think vector database. They hear vector database today, they think vector search. It turns out vector search indexes are actually closer to machine learning models than they are traditional database indexes. I think a lot of people struggle with that. If you don't tune a vector search index properly, you'll get garbage results. If you don't spend time tuning a regular database index properly, it might be slow, you're usually going to get great results. So I define vector search as a subset of machine learning that includes indexing vectors and performing fuzzy search, often by exploiting spatial locality. So it uses math and it uses geometry to find the closest vectors. It encompasses the fuzzy search, both sparse and dense, clustering algorithms that are used to establish spatial locality, approximate nearest neighbors is kind of the underpinning for vector search, and it also includes vector databases, but it is not equal to vector databases. So what is a vector database? Well, the vector database usually built on top of the vector search algorithms. They add many different features that you would see in production right today. Scalability, durability, availability. These are things that many people have done for years before there were vector databases on their own. Now there are formal databases for people to implement these much more quickly and not have to do the same thing and reinvent it from scratch. So they often provide guarantees as well with regards to consistency, availability, stuff like that, data freshness in the face of constant ingest. So the GPU is not always effective for every problem. And I think, you know, as a company, we have traditionally been associated with the AI movement. So obviously neural networks, deep neural networks, everybody's using GPUs for that these days, at least for the training. I have been in a part of the company, and I'll get into the actual org that I'm in later and the software that we build, but I'm in a part of the company that focuses on what we call the data processing layer. Turns out GPUs are really, really good for doing data processing. For doing menial tasks, we have strings libraries. For doing variable length string processing, we've got it all. Over the past 6 years, we have built so much. Vector search was kind of a natural next step. So we find that GPUs can increase the throughput, the amount of vectors that you can push through an index at the same time in query. It can decrease latency. We've found tricks that we can even do over online use cases where you only have one vector at a time and you want to get really low latency. Index building, we find, is what nearly everybody is interested in, because that's just like training machine learning. And that's a huge batch algorithm that we can crunch through really fast. What a lot of people don't know is that in the cloud, especially, we can lower costs, right? And since the index building can have a well-defined point, right, you can allocate resources for what you need, and then you can give those resources back when you're done and save some costs. You can do it in much less time, you can do it faster. So just some kind of paradigm differences here between the programming models of CPU and GPU. You can kind of think of a CPU as a Corvette, right? It's faster per core. You're generally never going to have as many cores as a GPU has. A GPU is more like a tour bus. It can, it can do a lot of things at once. It's not going to do it as fast. The concurrency implementation with CPUs, we're all familiar with threads and threading. Multi-threading. We use CUDA streams to do something similar in the CUDA world, where you're submitting kind of a job that we call a kernel. You can submit multiple kernels in parallel as long as there's resources to submit them and they can run concurrently. The CPU is best when used when you're doing pointer chasing. Oftentimes when you're traversing a graph, you have completely random access to memory because the graph's somehow not stored contiguously, which is usually the case. But when you have heavy compute and massive parallelism, the GPU is the way to go. Query performance is done through threading. Generally, we prefer batching using the CUDA streams with multiple threads in the CUDA world. Obviously, the best possible query that you can do on a GPU is when you have 10,000 vectors and you need to get all the nearest neighbors to those 10,000 vectors at the same time. We can do it all at the same time. And build performance is also done because we can batch as well. So now, who here has heard of Rapids? Anybody familiar with Rapids? We got one, two. There's not more. So Rapids has been around for about 6 years now. It is our GPU accelerated data science ecosystem. Rapids is huge. It's very important to us at NVIDIA. We've got a lot of mileage out of it, even internally. We're seeing a lot of increasing community. Essentially, you can think of us as libraries that are GPU alternatives to the popular high-data data science libraries. So scikit-learn, we have cuML. For pandas, we have cuDF. For NetworkX, we have cuGraph. And now we have cuVS, right? And it doesn't have a CPU equivalent, but we've started kind of expanding the ecosystem as we've seen the needs continue to grow. And so this is what our stack looks like. This looks like many of the different Rapids libraries. We expose different APIs at the top layer for doing integrations or for users to use directly. We have Python APIs, we even have Rust APIs, C APIs, C++ APIs. We've got a set of primitives that we build our stuff off of. We expose those primitives as well for other people that want to use building blocks to build their own algorithms. Underneath, we have a library called RAF, which we had originally built as a set of machine learning building blocks as we were building cuML and our cuGraph libraries. So there's a lot of nice low-level primitives there for folks that kind of want to go low level and integrate at the C++ level, but they don't necessarily want to have to write CUDA kernels. They're not easy to write. We have these guys that we call CUDA ninjas that work at NVIDIA. Their formal title is DevTech, but they're extremely good at writing these kernels, and they're willing to take on the burden of continuing to update these kernels as new architectures are released, so that you guys can use this code and just know that it's going to work the best on whatever you're using. And then obviously at the bottom layer, we have all the CUDA libraries. cuVS came from RAF. We started with RAF when we were building cuML, and we started realizing, okay, nearest neighbors is super important to machine learning. Right? It's important for subsampling, it's important for classification algorithms, it's important for clustering, manifold learning, dimensionality reduction. So we really started getting good at building approximate nearest neighbors algorithms when we were building RAF. And then OpenAI started coming out with ChatGPT, LLMs, RAG, everything blew up and we realized how important that got. And so our approximate nearest neighbors outgrew RAF, and that's when we decided to create a library called cuVS. It's an top-level library. CUDA vector search is a lot easier to market than a library called RAF that happens to be the same name in many other different implementations of different things. So we are currently in the process of migrating things from RAF to cuVS. We were hoping to have that done in August. We're going to finish it in October, but it is still fully usable today. We're no longer going to be updating things in RAF, but RAF does have the more feature-complete versions at this point. So as I talk about RAF and cuVS, I'm going to be saying cuVS, and I'm going to be kind of using that in place of the fact that RAF might still be the library that you want to go to today if you want everything that we have to offer. several algorithms. This is kind of the standard algorithms that you would have in a vector search library. It starts with brute force, which is the most naive. Exhaustive distance computation that doesn't scale particularly well, but it can be really fast for smaller data sets. It's pretty much exact, some non-determinisms when there's smaller values of k, but IDF flag and IDF PQ can partition the space. PQ can quantize the vectors to shrink them down so you can fit more. And then we have this novel algorithm, and we published a paper for this as well called Kygra, which is our kind of answer to HNSW and graph-based methods. It's built from the ground up for the GPU. Unlike HNSW, we try to do as much in batch as possible. So it's not a hierarchical graph. It is a fixed degree graph. It is a flat graph. I'll talk about it in a little bit, but we have found good ways to integrate with HNSW so we can build a graph. It's a Kygra graph on the GPU, and we can convert that into an HNSW graph. But Kygra right now is kind of our answer to online search in the vector search space. So Kygra is good at both large batch and what we call large batch. This isn't usually a thing, right, in the CPU world. We talk about large batch, we mean literally submitting a bunch of vectors at the same time, which if I need to compute a clustering, or I need to do manifold learning, many algorithms in QML do this with offline search. I've got 1 million vectors, I need to compute the nearest neighbors for them. This can crunch through those, but it also excels at that. I have a single query kind of trickling in, I need to find the neighbors really fast. I linked the paper there if you guys want to check out the paper. It just recently got published. So a few benchmark numbers. We like showing benchmarks. We're constantly running benchmarks, so we always have something to show. But we like showing these, multiples of tens of speed up. Speed up obviously is important if you consider the recall level, right? Research. You want to know how accurate that model is going to be. I can give you numbers all day that say something like 500x, but about 0%. So we tend to target these kind of buckets, 90%, 95, 99%. And so you can see here, we're well into the millions in our searches. This is for doing 10,000 vectors at a time. So we call this large batch search. We can just crunch through this faster. We've given HNSW every opportunity, multi-threaded. We're using HNSW live in this particular implementation. So large batch, no contest. Small batch is a little bit more challenging, and that's really where we fine-tune Kygra so that we can parallelize as much as possible along the way. Try to make a little bit faster memory access with some tricks. Parallelize the distance computations as much as possible. So we do see some latency speedups here. Not quite as massive as the high batch, but still nothing to ignore. It's a little bit harder for most folks we're finding to justify deploying the GPUs for search, unless you do have high volumes or unless your latency is extremely critical. And there are different types of workloads where they are, ads pipelines, for instance, or stock pipelines. And so one experiment that we were doing was, hey, can I have a mechanism that would allow me to submit queries in multiple threads in what we call CUDA streams so that I can do all of these queries in parallel, but not have to submit them all at once. So this is kind of mimicking a typical deployment scenario where you've got queries kind of trickling in, but you want to make sure that you can fit within a certain latency budget. And we were finding originally this blue line here, that when we started getting up to like 8 threads, that blue line started trailing off here. Essentially, the performance, something was causing a bottleneck here. It was causing contention. What ends up happening when we're submitting these queries is we're launching multiple CUDA kernels, and we're trying to make sure that those CUDA kernels overlap. And for some reason, at that 0.8, you couldn't get any better. And so we decided to kind of flip the problem on its end a little bit. Instead of launching multiple CUDA kernels, we said, let's launch one CUDA kernel and then have the CUDA kernel itself do the scheduling, have a little job here and there so that it can start kind of processing queries as they come in. And this is where you see the red line that kind of has a little linear increase as we continue adding threads to the problem. The yellow line there is what happens when we submit 10,000 queries at once. And so you can see here, the big thing to take away from this slide here is that we've managed to get to the point where submitting in 10, 24 threads, you can reach the same performance, the same amount of throughput that you can get by submitting all of those 10,000 queries at the same time. So this is kind of like a new thing that we're working on right now. We're hoping to get this integrated into Milvus soon. This is a big deal. And you notice the latency here. Latency is not always the inverse of throughput, right? So we measure latency separately. This I was throwing together over here at the table because this is such new information, but this is in seconds and not milliseconds. But the latency stays very, very, very low through all of this. Tagger index build times are a big deal. Again, price performance numbers here. I believe, we ran these on AWS. We tend to do cost normalized numbers when we provide the speed ups. But these here, I think, are the raw speed ups. But you notice, I mean, there's just a huge gap, right? You kind of dominate the build times when you can build on a batch of vectors at once. There are methods for being able to do incremental builds as well. What's nice is that this works really well with the Milvus model because the Milvus model uses a design whereby it converts these big files of vectors over to vector search indexes all in kind of a batch. So this really works nicely. So we find a lot of people that don't want to adopt the GPUs for search. They want to adopt them for the build. Build is easy to offload. It's easy to justify the cost savings. Our answer to that is being able to build the Tagger graph on the GPU. And then it turns out these graph-based methods, as long as they're navigable enough, hierarchy allows you to add vectors quickly. There's some research that was published recently that kind of talks in amongst kind of the idea of hierarchy doesn't really work after 32 minutes. It doesn't provide a lot for you. Unless you want to add vectors, then you have insertion points. So here you can get the best of both worlds because you can build a graphic Tagger. You can convert it to the HNSW on the CPU, and then you can search that through HNSW. And we're finding actually, because of the hierarchical difference in the navigability, this green line here is the Tagger graph. And you'll notice that sometimes we actually get better throughput when we're searching the Tagger graph on the CPU using HNSW than we get with HNSW. So that was a nice find there. And we don't always see that. We see it in higher dimensions. We've recently released a modification to Tagger that we call Tagger Q. It's an option in Tagger if you're using cuVS. Tagger Q essentially compresses the vectors in the graph so that you can store more vectors on the computing device, the GPU, at one time. The other vectors end up getting offloaded. We do a refinement step so they still have to exist in RAM. This actually works really nicely with our Grace Hopper hardware too, because we have what we call a chip-to-chip link. Whereby we have an extremely high bandwidth between the host RAM memory and the device memory. And so this is able to take advantage of that. There's a GTC talk all about this if you guys are interested in learning more. It's a great talk from my colleague, Akira. Now about Milvus and cuVS. So this is the standard Milvus 2.0 architecture. We made some really, really complicated changes to it. You ready? So we basically accelerate the queries and we accelerate the index build on GPU. Now, being released very soon, I believe, is the capability to index on the GPU and then deploy to the CPU search. I think that's going to be in 2417, 2471, whatever the next release is. 2471, okay. So with Milvus, we wanted to see what we could do, because obviously we have to start investigating this early and see where we can go. We wanted to see how high we can push this. And this is a common thing that we do at NVIDIA. We do these weak scaling benchmarks. And this shows us how our algorithms respond to increased data load while you're increasing the number of processes. So it's kind of a complicated thing to reason about. But essentially what we want to see is this green here. As we double the number of GPUs and we double the amount of data, we didn't want this green to continue growing because that means that there's some inconsistency there. It's not a linear scale. The fact that this green doesn't grow means that we have a linear scale. As we continue doubling the GPUs, we continue doubling the data, the amount of time that it takes to build indexes does not change. The gray here, ingest, we didn't double the bandwidth, right? We didn't double the disk bandwidth, we doubled the number of GPUs. So that gray there is kind of meaningless here. But this linear scale here that we're seeing allows us to project. Now, we see here, this was about a 20x speed up. Okay, and that's going to mean something later because we use that to actually project because we didn't have time to wait for the CPU to actually run the algorithm. So we use a speed up that we get here knowing that that's a linear scale. We did some weak scaling also on AWS to show that we could. This is using Milvus. And you see this index creation time. This is, I ingested a bunch of vectors into Milvus without an index. Okay, I ingested all of my vectors, and it took this long to get all the vectors in there. It's 80 billion vectors by 1024. Then I said, now create an index, and we measured the amount of time that it took. So on the CPU, this is the amount of time that it took. On the GPU, this is the amount of time. And we're not done there, right? I mean, what this exposed us is that the disk I/O and network I/O are not the bottleneck. Before we turn the GPU on, they're the bottleneck. So that's the next thing we're getting to. But you know, ultimately, when we do things in cloud, we have a price that we can associate with this. Now we can measure price performance, right? So when we measure the CPU against the GPU, one way we can say this is that we build indexes 21x faster at a 68% higher cost. If we normalize the cost, then we can say that we still build 12.5x faster. Right? If we say that the two things cost the same, we're still getting it that much faster. So we decided to see how far we could push this, right? So we started with 1 terabyte of raw data. That's raw data. That's not 1 terabyte of vectors. We wanted to kind of simulate what a RAG flow would look like. We're very interested and intrigued by RAG in video right now. So everybody's talking about RAG. It's like the only thing coming out of most people's lips. So we simulated this by taking 1 terabyte of raw text. It's a lot easier to say I have this footprint of documents. Now I want to turn that into vectors than it is to say I have a billion vectors. That's meaningless. What dimensionality, right? So we say raw text. If we use a chunk size of 300, so we say 300 words, right? We don't split over sentences. It's a tumbling window that makes the math easier. It's a simple division. Okay, that turns into, once you do the math, about 635 times 1020, a million times 1024 vectors. Ingest took about 11.5 hours in Milvus. It's not great, right? We're working on ways to fix that. It's not great. We're trying to do some more stuff on the GPU there too. Where we start our thing here is we have 2.5 terabytes of vectors now. We did an explosion of 2.5x, right? We ingested all that in. Then we said index build. This is using our IBM DQ algorithm, so we can fit everything in device memory. We were on a DGX H100. That means we have 8 GPUs. It took 56 minutes to do all this on 8 GPUs. So it's parallelizing over multiple GPUs. This was a dual socket system. Okay, so on the CPU, now we did those prior benchmarks, right, with the weak scaling and everything. There was a reason for that. We had a 20x speed up with the weak scaling. We now know that that's a linear speed up. So now we can say, okay, we can project and we can say, how long is that going to take on the CPU? We didn't have 6 days to wait for this. This was something we did right before GDC. We had like 2 days. So we couldn't wait 6.22 days. But this is what we projected that would have taken on the CPU. It's a huge difference, right? You have DGX H100. You have, you know, and I think that kind of speaks for itself. But we're doing great things with Milvus today. We're continuing to push. We want to get to the 100 terabyte next, which is going to require us actually getting Milvus deployed on Spann. We're going to do that. We might try to contribute that back. But we've got like a supercomputer with like thousands of these DGXs, and we want to run it on that because we want to find out when we get to the petabyte scale eventually. Some other things that we encountered, so that really long ingest time, that 11.5 hours, we started doing some profiling of that. We decided to try to swap the min.io out with pure storage, which we used it in AS. It turns out we were able to reduce the upload time to the object storage by quite a bit. See the blue here going a lot smaller. That's the shrinking time there. So that's one thing. We're also now trying to accelerate end-to-end the min.io, the actual object storage, right? Can we bypass the CPU, excuse me, as much as possible using this technology we have called GPU direct storage? Allows us to essentially cut the CPU out of the mix. We have an initial negotiation that we do with the CPU to say we're going to need to read a bunch of data from the disk. And then the CPU says, okay, bro, go ahead. And then we just have a direct connection. And that's some other stuff. This is one of the things that Pure Storage is using here too. So some lessons we learned throughout all of this. We kind of learned the hard way. Some of these things were just as simple as increasing the number of data node processes that we ran on the machine. It didn't occur to us at first. But that actually really sped up. We noticed that we weren't able to saturate the disk bandwidth. So that helped us actually get closer to saturating the disk bandwidth. We don't have an overwhelming number of people doing Milvus on the GPU today. So we are trying to learn all of this and be more prescriptive. A lot of people are asking us for how to do it, right? We ran into some issues trying to place both the index and the query processes on the same GPU. So for now, we're separating them, and it seems like this works out the best, right? If you have on-prem hardware, this can be a little bit easier to do. If you have cloud hardware, I mean, it just takes allocating more instances. The NAS can improve network performance. Apparently they're telling us we need to leave. And increasing the, we also noticed in these long structured merge type of paradigms where you have these, the way Milvus works, you have these big segment files, and the segment files grow to a certain size and merge together, and then they convert over to a vector search index. It's not as costly to load 100 of those little segment indexes on a single CPU. It's a lot more costly when you need to do search to load them 100 of those onto the GPU. Because the query ultimately needs to be broadcast out to every single one of those, and they all need to be searched. And so it turns out increasing that segment size so that it kind of more aligns with the size of plan memory that you have on the GPU allows for faster search. So for some next steps, these are things that we've been working in our collaboration with Milvus, building the tag graph on the GPU and searching with the CPU. That should be out soon. Lower precision to be able to increase the amount of data and index sizes. Sparse nearest neighbors is something we've had in Raft for a long time. It's going to be moved over to cuVS, so we're going to expose that through Milvus. Extreme filtering can be challenging on the GPU for graph-based algorithms, and this is something that comes up when you're doing hybrid search, for instance, and you go dig into your SQL database or your NoSQL database, and you have like 3 records out of 1 million or 3 records out of 1 billion, and you now need to filter your vector search index for like 99% of the data you don't need. That can be really challenging. It can drop recall. We have a pre-filtered brute force that only computes the distances for the vectors that are, supposed to be included. And so we're going to kind of make that transparent by adding that to Tigris so that when you're filtering out 99%, it uses brute force. And of course, we want to be able to support hybrid search so that people have full capability. So we're integrated with Milvus, and we're by far our closest partners are Milvus, and we love them. We have a lot of other integrations going on too, and we've been very good friends with FaZe for a long time, and we work very closely with Meta. Ideally, the next step for the Milvus integration with cuVS is going to be through FaZe. So right now, cuVS is integrated into FaZe, so you can use it with FaZe, and you can use it with Milvus. You can also use FaZe through Milvus. What we would rather do instead is have cuVS integrated through Milvus so that you can use cuVS. So that's going to be a next step there. Kinetica has integrated cuVS. We've seen is like the 800-pound gorilla in the search space, so of course that's a no-brainer. We're actually working very close with a company called SearchScale. A bunch of Lucene committers. We did a talk at Early Buzzwords. If you guys are interested, it's very well received. We're hoping to make a huge impact there too. And so here's some resources. All the rapid libraries are free and open source. Access to licenses from GitHub. We love hearing from users in the community. So if you guys have, you guys use our software, you can go to feature requests. You just want to come chat about cool things if you know, we'd love to hear about it. Come give us a star. And yeah, that's it. Thank you. Anybody have a question? In terms of accuracy, yeah, I think it depends on the precision that you need. Because, for instance, an image, you can get away with like 8-bit, right? Yeah, that's the point. Yeah. Right, and you don't suffer any accuracy loss. And I think images are like a big use case. There's other ways that you can make up for the precision, right? Where if the goal isn't necessary, so there's 2 things that you get from lower precision, right? There's the benefit of doing vectorized instructions on the lower precision hardware, and then there's the ability to process more data. If you care about more data and you don't necessarily care about the mixed precision of having to do the lower instructions because you want that precision, you can do that too. Yeah.
So I noticed all your examples were on current generation hardware. How does cuVS, Tableau, etc. from here, there's lots of hardware, and here we need lots of hardware, and it's kind of going
Volt is actually the minimum that we support now. So it is kind of getting old. It's still great. I mean, you still get parallelism. You know, we obviously always try to use newer generation stuff, but some of these benchmarks I also did. I think that one of them was on T4. I think. Yeah, there's definitely still benefits, but I will say too, like we're having a conversation with Google, right? And like they saw a blog of ours that was on H100 talking about how we have like significantly lower latency at single query at a time in HSW. So they ran some benchmarks on a T4 instance, and they're like, this isn't faster than Spann. And it's like, well, come on, that's what they teach, you know. So I mean, yeah, I mean, it definitely scales the performance down, but I think when you compare to like cost-wise to a CPU in kind of the same price point, we tend to find that the GPU can be used faster still.
Hello. Thank you for this talk. And I just wanted to ask if this documentation will be available to us, because I saw a lot of links available in the resources.
Yeah.
They seem to be clickable links. So will this documentation be available to us after the session?
Absolutely. Yeah.
Thank you.
Anybody else? All right. Thanks, everyone.
That was pretty awesome. No.
I don't compiling this stuff. I don't know that there's been like thorough benchmark. For disaster, but I'm here for it. Okay, so for the next section of this, I'm going to be walking through. Feel free to follow along. Or just follow by watching the presentation. But the tool that we FiftyOne open source story to do a lot of data. Place the main version of why this is so valuable important. Hugging Face is awesome. And I was going to save this for the end, but by the way, we also have an integration with Milvus. Yeah. The FiftyOne docs or the Milvus docs, and check those out there. A lot of those companies, we have a ton of cool applications, plugin and otherwise built on top of that. I'm going to show you a little bit of that vector search stuff in FiftyOne momentarily, but let's get into the data. Okay. So I've got a notebook up here. Let me increase size so people can see. If I put that there, okay. All right. I'll just click the buttons to go through the cells, and hopefully that'll be good enough. But 1 second. Woo. Got too lucky. Okay. And in the meantime, let me show you
This is FiftyOne. It is an open source library. You can view all the source code right over here. Doesn't have quite as many stars as Milvus, but still 8,000 stars. It is available via PyPy, so if you write Python code, you can just install it via the Python package manager. You can check out all of our docs, all of the tutorials, blog posts, tons of resources there. And here's Hugging Face, which everybody is probably familiar with. This is the place where everybody shares their models for large language-based applications, for visual things, just any types of models typically that are transformers or diffusers. So GPT is a transformer. That is what the T stands for in GPT. This is part of this new wave of AI that has become so powerful over the past couple of years. If we go to Hugging Face, we can see they've got models. We can actually filter by them. They've got data sets. They've got spaces and tons of other things. And you can even go to this libraries tab and see a bunch of data sets that are in FiftyOne format that you can just download there. But we are going to go to the notebook and start coding. So we're going to install a few libraries. We're going to install the Transformers library from Hugging Face, the Hugging Face Hub library. This is going to allow us to pull things and push things to the Hugging Face Hub, and then FiftyOne. The last thing is just UMAP, which is a dimensionality reduction technique. Like PCA, you guys are familiar with principles of dimensionality. It takes these high-dimensional things and allow you to find some lower-dimensional structure in them. You can then use to visualize and interpret the result. UMAP is just a little bit smarter in some ways, preserving the global and local structure. So lots of talking. Let's actually code. So the first thing we're going to do is we're going to import some stuff. We're going to import FiftyOne, some modules in FiftyOne, lots of imports there. Now let's load a data set. So FiftyOne has a zoo that has a bunch of default data sets. Too far, photo, images to download, any of those without having to do any custom importing. You can also load your own data, as we'll show momentarily. But then you have this data set object, and we can print it out and see what's going on here. Oh, what happened? Trying to do too much. We can see a preview of what this data set looks like, and we can see these fields right here. So this is the semi-structured stuff I was talking about. So you have some attributes, some IDs on everyone, file path, tag, metadata, but then we have things like this ground truth or predictions, which have some nested or embedded semi-structured data within them. But let's actually do something better and just visualize the images themselves along with all this metadata. We can do so by launching a session. So often with this type of semi-structured data, especially when it's visual, it makes sense to just literally look at it. And so this launches an app, which is just going to open in your browser. You can also open it right in a notebook. And just to clarify, I'm running this in a VS Code notebook, but you can also do this in just a Python process, a Jupyter notebook, in a Databricks notebook, all over the place, Colab, wherever else. You can see the app here. I find it easier to work with the app in a tab in my browser. So we're going to do that. And we're going to load. We're going to go over to this data set that we just created. And we can actually scroll through it and visualize these images. We can click into them. We can see what's going on. We can inspect the predictions, the ground truth. We can filter. So let's say we just want to see things that have a person in them. And we want to see things that, let's say, have a prediction of a height. And then we can see all of those images right there. We could even filter by prediction confidence. And this is just one example that shows detections with certain confidence, but you can filter based on any of these attributes. Either they can be custom attributes that you define, or they can be some of our built-in semantically meaningful attributes. So we're visualizing this data. That's great. What can we do with it? Well, one thing we can do with it is let's reset these and let us compute an index on this data. So we go to this. All I did here was I pressed this backtick button on my keyboard to open up this panel. We can compute similarity. So let's say I want to select the entire data set. I'll just do call it clip sim. We're going to use a model So let's use a clip model here. So what this is going to do is it's going to go through all of our images, going to take a clip model, which is this multimodal model, with images and text. It is going to pre-process necessary images, going to generate the vectors for them, and it's going to put them into a vector database, put them in query. So now that we have that, let's first do an image similarity search. So let's take this, let's just do a checkbox here. And now let's click on this button up here to show similar samples. So what that's doing right there is it's like a GUI, this UI where we can utilize the vector database for our visual data. We can take that image and then it's going to look up the vector associated with that and do a query with that vector as the query against the vector database and show us all the images whose results were the most similar. We can set a threshold, we can do lots of fun stuff. Here I didn't set a threshold, I just told it, give me like the top 25 examples. But we can even do another example with a text-based prompt. So I could search for kites flying in the sky. So now it's going to take that text, it is going to embed the text, compare that against and here we don't get too many results because data that only has 280, but this scaled up to however large it is. You can also do this on passive themselves, so you can objects in an image and font and then search only objects for text or visual query. Cool. So this is just a dummy example. Now that we have this data set from the zoo, that's great. Zoo only has like 30 data sets in it, but where do we have more data sets? Where is like the hub for a lot of new data sets these days? Well, Hugging Face. So Hugging Face has all these data sets that are in FiftyOne format, but they also have data sets which are just in Parquet format. So when anybody uploads a data set to the Hugging Face hub, it's typically uploaded in Parquet, just in efficient format for processing all various different data. And that may not be the best thing for interpreting and actually being able to parse and filter and query our visual data, but this is what people do. And fortunately, we can take these data sets that are in Parquet format and actually convert them automatically into FiftyOne format. So let me go here and let me choose a task. So let's say I want to do an image classification task. And I'm going to look at the data sets by trending. And I can see the data sets with the most downloads. And I can see this whole list right here. So there's some things that we're familiar with probably, like CFAR. We have ImageNet, we have MNIST. We've got a bunch of other things. So I'm just going to choose this one right here. This is the WikiArt data set. So it's got a bunch of art images. So these are pictures of paintings in various styles and various art. And we can see they have this little preview of what's going on in the data set. We have these few images and we have these categories associated with them, but this doesn't really give us the ability to interact with the data. Never mind actually process on it or train a model, because first we need to understand it and then maybe filter it and maybe find the bad images or find the subset that we're interested in so that we can train a model for our particular use case. So we can just take this data set, we can take the repo ID here, just this person's name and the data set name for this repo. We can just plug those back in to our code over here, and we can load, where is this? Aha, okay. And we can just load this data set directly from the Hugging Face hub. So we just got to specify the format is in Parquet. It's going to take it. It's going to take these classification fields, these features in the data set, and it will turn those into classifications in our terminology. And here it's going to download and create this data set object. Should be pretty quick here. I'm just taking 500 samples, but you can do this with thousands, hundreds of thousands. We have people who do all types of things with this. Now that we have this data set, we can print it out as we did before. We can even inspect certain elements of it and look at what the structure looks like. And we can see this taxonomy. We have these classifications. This one was actually painted by Vincent van Gogh. This one is a realism and landscape. We can look at the second one. We can look at any we want, but we can also just go back over to the FiftyOne app and visualize it as we did before here. So now we have all these images, and not only do we have images, we have all this metadata associated with them. So I can like filter by artist. I can filter by style. None for that. Let's see, a couple for this. I can see all of the images that were realist and were painted by Vincent van Gogh. So now I have this ground truth data of sorts. Maybe I want to filter it. Maybe I want to just select images that are painted by Vincent van Gogh. Or maybe I want to do something else. In this case, actually, I want to apply some models for data. So Hugging Face has all these models for lots of different tasks. And we can do things like take one of their classification models and apply it. And if you were just to apply this in a standard way, you would have to go through this whole rigmarole to take your image, to go through your page, to process it, to make sure you're not properly getting all the gradient, and then you would get your results, then you have to post-process the results, and make this for all of your images, and so forth and so on. This would change based on which model you're using, based on what task you're doing, based on a lot of different things. But fortunately, you can just apply these models to our data sets without any issues. So we can just take this model, load it. So this is a model straight from Hugging Face, and we're just going to apply it. And here I'm just going to apply it to the first 10 samples in the data set. And now I'm going to go back over to the app. I'll hit refresh. And now we can see that we have these labels on it in this new field that we just created. We can even see the confidence in that classification. Now, this is just classification, but this also works for other things. So we can apply, for instance, a depth estimation model like depth anything, which has been very popular recently. So here I'll do this again just for the first 10 images, so it'll be really quick. And this is happening all on my CPU. If this were on a GPU, like an NVIDIA GPU, this would be far, far faster. So apologies for my slow nap CPU over here. But we'll see we have these images that we are running predictions on, we're running inference on, we're going back over. And now we should have this depth field over here. Yeah, so we can see the depth that it generated on our images over here. And we can interact with this depth map as well. So we can go back over and we can say, let's escape from this and let's do dataset dot first. We can see the map over here in the heat map, and we can actually extract that, and we could do computations on that, we can do lots of different things. We can generate data sets from Hugging Face for other tasks as well. We could just take a detection data set. So here, I'm just going to take 500 images from this detection data set of personal protective equipment. And now let's load that in. So let me go over here. Let me actually just refresh and show you how you can actually do this from the app as well. And everything I'm doing in the app, you can also do via code. There's a seamless integration. So any change you make in code will propagate to the app and vice versa. And every operation that is happening in the app is just a wrapper around an SDK that Python. We have these images now, we have detections, and we can do a lot of things with them as well. We can also run models for other tasks. So if we're interested in more multimodal things, we can use image captioning models or V2A models. Oftentimes they're from Hugging Face, other times they're from different providers. Sometimes they're from endpoints like Replicate or Fireworks AI provides. You can use any of those. So here's a plugin to FiftyOne that allows you to do that with some image captioning things. We've got some VQA, visual question answering, which allows you to ask a question about your images. So plugins for that as well. So I'll show you what that looks like. So I can just go over here and I can click on this and let me just type in VQA, and I can choose what model I want to use, and you can add your own models, you can do whatever you want. The point is just that this makes it easier to connect your models and data. So I can ask, like, what is the person doing? Let's see what it tells me. Now, these models are not perfect, but it says the person is wearing a mask, like a surgeon, and looking through a microscope. So maybe that's correct, maybe it's not. We are inheriting the biases of the model when we do something like this, and we have to be aware of that. But the point is just that we can now have this UI and an SDK via which we can connect the models and the data much more easily for whatever business tasks we want. We also have integrations with GPT-4o and lots of other things. Now, I want to show you something else here. So let's go to, let's actually go back here. Let's go to the WikiArt dataset again. And we use the vector database with these embeddings that we generated to do similarity searches. But I mentioned at the very top that we were installing UMAP, which is this technique that allows us to visualize the data. So let's just take these embeddings that we generated and visualize the data. So I'm going to compute visualization here. And there's no magic going on. These are all open source. You can see the code for all this stuff. And you don't have to use clip models. You can use whatever models you'd like. Any of the models that expose embeddings in Hugging Face or in the OpenClip library are possible, and you can also use your own. But let's just call this clip viz, and I'll use embeddings. Oh, I didn't save them before, so I'm just going to do it again. But you could just save them, and you could prevent having to deal with all that. Should be pretty quick. So it is going to run this on all of our images. It's going to then take all the vectors and find the relevant information in them, find the structure in this data set. So it's going to try to optimize the peak, both local and global structure, while getting a very, very small dimensional, essentially manifold. And in this case, it's going to do a two-dimensional manifold. It's going to project this into approximately. So this should be done very soon. Again, this is not on GPU. Yeah. Amazing. So I usually SSH into a computer to run on a GPU, but there's enough writing on probability, and with live demos, you never want to take too much of a chance. But yeah. Yes. Yeah. So here I've just opened up a panel. You can also create your own panels, but here I just opened up a panel, and I'm going to take this key where I saved my results, and now I can color by whatever's going on here. So to just explain briefly, I have this panel which has a 2D point for every one of the images in the data set. You can also do this for each of your objects or lots of other things, but each of these points is corresponding to an image. So let me actually just lasso select one of these clusters, and you can see what's going on there. We can select a different cluster, keep on going. We can even color by certain things. So let me color by, for instance, the artist. We can see kind of how this clumps together or doesn't based on the artist or based on whatever the category we want. We can also combine this with filtering. We can run clustering and then have the names. We can actually, using GPT-4o, auto-generate some names for each of the clusters and then project those onto each of these as well. There's lots that we can do here. But the cool thing is this gives us some intuition for why we're going to run a semantic or a visual similarity search on our images. We would get certain results that we do. So I can say, where is this one? This one's over here. So if I take this and I run I've got a, damn it, I keep on forgetting, but I should have saved the embeddings and then computed a similar research based on that. And then we can see all those results show up over there. And it's not one-to-one because this visualization is in 2D, but the vectors are in this case, 512 dimensions. So it's not going to be perfect, but it should be pretty close. It should give some intuition. Actually, you know what? I am going to just do it. I'm going to compute similarity real quick. So apologies for this. Sim So yeah, bear with me for 10 seconds while this computes, and then I'm going to show you how this corresponds, and then we'll do one more thing, and then I'll just show you a bunch of other resources, point you in a bunch of directions, and we'll be on our way. We've gotten pretty lucky with the structure. The classification is what? C or whatever other classes it's set to those classes to create your own model. Or you can use a zero-shot model and specify your classes that that's currently. What? Try this one more time here. This one. Now let's do a similarity search. So now we see all these results over here. So now let me just click on all of them. We can see where all of those appear in this visual relative to our image. Now we can also do something else here. So there was a mention in one of the talks about reverse image search. You can do the same thing here. So why don't we just open our reverse image search panel, and let me just choose an image from the internet. Let me just choose this one over here. I'll just copy the link. Now let me paste it in. You can also use files that are local on your computer. Hopefully this will work. There. So these are what it thought were the most according to this particular embedding that we use, but we can use whatever we want. And in fact, I've got another example pulled up here. I've got generated dogs. So this is using Stable Diffusion, which is a model that takes your text prompt and it tries to generate the image that matches that text prompt. So I've generated a bunch of dogs in the categories of the Stanford dogs dataset. And now I can, as we were doing before, I can run an image search on this. Or and again, open up this reverse image panel, and he wants to give me a dog breed to type in here. What did you say? Brittany. I've never heard that before. I'll do a golden retriever. I don't know how to spell that. Golden retriever. I like this one. We'll choose this one. Here. Let's see what shows up. And this is going to show us something else interesting, which is it does a pretty good job, but there's probably not going to be exact overlap because these are images that are generated, so they're from a different distribution than natural images. So when you embed them, probably they're going to be kind of far away potentially from real images, but you still get pretty good results here. The point is just that this allows you to better connect your data in your models. You can do lots of interesting things. You can understand what's going on better. You can test out your models. You can visualize the data. You can train better models in your day. That's it. I don't know if that was the time. Was that time?
Pretty close.
Okay, cool. Yeah.
That was pretty cool.
Yeah. So lots of other things, text to image generation you can do, so you can actually generate those images directly in the contents of the data set. Zero-shot prediction. You can use transformer models directly from a plugin in the UI. And when you're done, you have a data set you're comfortable with whatever results you want, with whatever subset you want. You can just push it back up to the hub. So we can just use our push to hub function Then we can specify the name we want, specify what we want, and it'll just add it directly to your user profile or whatever your organization is on Hugging Face. And then it will appear in the list and everybody else can download it and work with it. So that's it. Here are some resources. They're in the notebook. I also have some resources here.
You're gonna give us all, you can give them to me.
Yes.
I'm gonna post them in the Meetup.
Yep.
In the Lumen group. Follow-up email, share your YouTube channel.
Yep.
The slides, storage code. You're gonna get like probably 30 pages.
Great.
So be prepared. That's not spam. You ask for it. If you don't ask for it, unsubscribe.
So feel free to give us a star. This is a open source free project. You can follow us on LinkedIn. We just passed 10,000 followers. You can also try it out for free in your browser at try.FiftyOne.ai. Tons of cool stuff. You don't even need to download and install it to give it a try. We have something called Voxel GPT, which allows you to do all this stuff just using natural language queries. It'll turn that query into the code to actually perform the operation on build and query data set for you. It's a really, really rich ecosystem of content, including our integrations with other partners in the open source community like Milvus. So I hope you enjoyed, and thank you.
That was pretty awesome. And again, open source. Gotta love that. Gotta love all those really cool examples. I am definitely gonna try them out. We will share them with you. Send them to me. We'll get them out to everybody. Anyone who asks a question, we come up with your answer. We get a company shirt and one of this guy here. There's stickers for everybody. We could either, we got a couple options, we could do a couple more questions, and we get a little bit of time. We could do a little networking where I can show you some really intro and video going way deep into you show us everything in a few seconds. But like everyone at home, yeah, I'm just gonna go into the notebook and little things bottom. Very easy. But it was awesome. It was awesome. I mean, I definitely got to play around with your stuff there.
I hope you do. And feel free to reach out if you have any questions. Myself and other people at the company are always happy to answer. And we have a really, really helpful Slack community. So we've got about 3,500 people in our open source Slack, constantly asking and answering questions related to everything data-centric AI, ML. So, getting all the big model training, have to be the second to last layer to that layer, you get big second space. Should be able to for CVPR, which is like the big computer vision conference that happened months ago. We actually scraped all the papers that were at the conference and then embedded them using text embedding model, not image embedding model, and put all like images of the actual papers with the text embeddings up on there so you can do that data set and see how flexible it is. So you can add whatever customers want. I don't think we currently have like specific support for knowledge graphs built in, but if you want to build it, go for it. It sounds really cool. It's definitely really. We have just added the functionality for people to link from one to the next, so you can really like put the URL of something in and have it linked back and forth. So yeah.
Sure. Next week. Yeah. You're looking for, let's see what in the past we worked. Let's see if it can be applied to. Then how can we make that data visual?